Okay. So good morning, everyone. Thanks everyone for joining us on this webinar. This is one of the series of webinars supported by TV Care 2, USA funded TV Care 2 in collaboration with NTB Transmission Initiative, ATTI. Today's webinar will be on applying germicidal UV to control spread of airborne infections, microorganisms in an era of COVID-19. We have 4 sessions, actually three sessions or presentations by our experts. We'll start the first one. I have on the agenda Ed on the first one, but on the presentation I have Carrie. So
I need to go first because I have another webinar to go to. Yeah.
Okay, thank you, Ed. So Ed will start with the first presentation and will be on basics of UVGI, what is efficacy, safety, etc. So please proceed, Ed. Thank you very much.
Thank you. Thank you all. So I'm going to talk about germicidal ultraviolet. Normally, of course, we're talking about tuberculosis. And there, the issue is quite clear. We know that tuberculosis is exclusively airborne. It's rarely passed from person to person any other way. And so air disinfection is a logical choice. With COVID, the role of airborne transmission is rather controversial. WHO had initially said that was really not airborne and spread only by droplets and directly and indirectly. But little by little, that position is changing. First of all, CDC was recommending respirators, we'll be talking about those later, for N95 respirators for healthcare workers, which of course is a precaution for airborne infection. If we're just touch or droplets, normally surgical masks are sufficient. And then, of course, now WHO is taking that position as well, recommending respirators rather than for healthcare workers. So there is a little bit of mixed messaging going on. There are examples in the literature of transmission that certainly sounds like it could be airborne. A choir in the western United States where many people were infected in a 2.5-hour period, none of whom were symptomatic with cough or sneezing. And the question is whether or not there was an airborne component. In Wuhan, China, there was a restaurant exposure where infection went from table to table. Again, conceivably large droplets, and perhaps we make too big a distinction between large and small droplets. They can both be carried by air some distance. So I'm going to be talking about UV. I don't have a lot of time in this particular presentation, and I'm trying to see how to advance. My button is not doing it. Is there a button on the screen? Okay, thank you. So, in much of the world, of course, we depend on natural ventilation, and it's essentially free and can be highly effective, but it is highly dependent on conditions. I mean, in some parts of the world, like Lima, Peru, and Karachi, Pakistan, there by the sea, there is a lot of continuous breeze, but it's not always present in many other parts of the world, and certainly not in cold climates where you can't open the windows, and increasingly, as you'll see in a minute, in hot climates where it is so, with global warming, where the temperatures are such and humidity is such that air conditioning is being used, and that limits natural ventilation as well. It is perfect for outdoor waiting areas in climates where that's possible. So if you think about what you could replace natural ventilation with, there really aren't a lot of choices. if you have to replace or supplement natural ventilation. Next slide. So I mentioned global warming and the growing use of ductless air conditioning. Ductless or split system air conditioning is shown here on the slide. I don't know if you can see my arrow, but there is usually on the wall a unit that allows coolant to come up and down from an outdoor condensing device, but there's no air coming in. So this is recirculating air. And even in what's more like a window air conditioner where you can have some outdoor air come in, it's not very much. So anyway, when you turn on air conditioning for efficiency, you don't want to cool air and then have hot air coming in the window. Windows must be closed. This chart on the right here shows air conditioning sales in India from 2010 to 2015, and this is largely true in many warming parts of the world where money is available to buy them. And you see a very steep rise in the use of air conditioning. And with every one of those air conditioning, including in healthcare settings, windows are closed. Next slide, please. What happens when you close the windows? I won't go into great detail in this little demonstration that's published, and you see the citation underneath the figure of an editorial published this year in Indoor Air. But these are 5 people in an office with the window open, and you reach a equilibrium of CO2 levels. CO2 levels in the room are generated by the people. CO2 is generated by the people and diluted by the window air, the ventilation coming in, and you reach a level that's higher than outside but lower than it would be if the window were closed. And in fact, if you turn on the air conditioner and close the window, this is what happens to the CO2 in what's called phase 2. You see a steep rise, and just an hour, the CO2 level doubles from around 500 to actually almost triples from 500-600 to around 1,500. And that would be associated, the doubling would be about twice the risk of infection. A doubling again would be again twice the risk of infection. So you see that when you close windows and turn on air conditioning, you increase the rebreathed air fraction, the percentage of air that you breathe that somebody else has already breathed, and the risk of indoor infection. That could be tuberculosis, and to the extent that COVID is airborne, it could be COVID as well. Next slide. So what are the alternatives? On top, I have a rather typical air cleaner, and this is a device, usually some sort of a box with a blower in it, and often heap of filters, sometimes ultraviolet, sometimes other methods of destroying microbes, viruses, and bacteria. And air in this one probably comes in here and goes out the top. And these are widely sold in all over the world, and salespeople will tell you how efficient they are in removing the microbes from the air. 99.9% efficient. That's very true. The real issue is how much air goes through these devices, and often that's very little relative to the volume of the room. It's called the clean air delivery rate, and oftentimes such a device in a room, and I'll show you an example, might give you 2 air changes per hour in addition to what you have, and that just isn't sufficient. Mechanical ventilation, if you have it, is a substitute for natural ventilation. But if you don't have it, you're not likely to put it in because it requires quite a bit of ductwork, etc., and is fairly expensive to operate and has limits in terms of the numbers of air changes it can produce as well. It is used widely in resource-rich countries, such as the United States. Most buildings have mechanical ventilation. Finally, in the picture below is a UV fixture, a wall fixture, and you see the blue-green light behind a number of louvers designed to keep the UV ultraviolet above eye level. Next slide, please. So here's an example. This is a meeting in 2016 in Pretoria, and a salesperson for a room air cleaner was there. And we looked at the air cleaner and found out what its clean air delivery rate is CADR. And it was 60 cubic feet per minute, or 28.3 liters per second, which in a room, a small room, 4 meters by 4 meters by 3 meters high, would deliver 2.1 air changes per hour. And that assumes that there's no recapture. What I mean is that air that was just processed through the device gets retrapped again in the intake and goes around and around, and that doesn't really contribute to air disinfection. So assuming no recapture, 2 air changes. If we put upper room germicidal in the same room with easily achieved levels of disinfection, we could add approximately 20 air changes per hour. So really no comparison at all. Now, are there air cleaners that could reach that? Yes, in this case, you'd need 10 of them with this device in this small room, so that's not very practical. Next slide, please. With upper room germicidal UV, the reason it works so well is that we disinfect a huge amount of air at once. Here in the schematic diagram, you see the beam of UV going across the room, and we try to cover as much of the upper room as we can, and we depend on room air mixing. Here, you're seeing just body heat generating warm air that goes up, and then it cools and comes down, but we get even much better air disinfection throughout the room by employing low velocity ceiling fans to assure good air mixing. So the reason we keep UV above the people's heads is that it's irritating to the eyes. So it's not dangerous. This is not, UV, as we'll see, doesn't cause skin cancer or cataracts, even though some people will confuse it with sunlight, which does. But UVC, germicidal UV, does not cause skin cancer, does not cause cataracts, because it doesn't penetrate to the lens of the eye, and it doesn't penetrate the skin down to the basal layer, which is required for causing skin cancer. It does cause eye irritation, which is if it's applied inappropriately. If you keep it above people's heads, you don't get that either. So it's safe to use in occupied rooms. Next slide. So here's a comparison of a study. Grigory Volchenkov from the Vladimir Oblast TB dispensary head doctor, in conjunction with Paul Jensen, who is not on our webinar today, but Gregory is, did this study some time ago where they compared the efficacy and the cost of disinfecting air with 3 different air cleaners that were available in Russia: mechanical ventilation, accounting for the cost of putting it in and the cost of running it, and UVGI. And this is in the upper right corner here is a very simple UV fixture that Grigory employs in the dispensary in Vladimir. And you see that the cost per equivalent air change is extremely low for UV compared to mechanical ventilation or any of the 3 air cleaners that were employed. And if you talk about relative efficacy and cost effectiveness, it's over 9 times more effective, cost effective than other means of air disinfection. Next slide. Now, I haven't mentioned surface disinfection, and we need to. I'm not going to go through this very detailed slide, but there have been a number of barriers to scaling up UV to the level that some of us feel it should be. One of them is proof of efficacy, fear, having good dosing guidelines. Could you go back, please? Dosing guidelines, expertise. Who do you get to explain how to do this and help you do it? Good fixtures, solid electrical supply. Air mixing is very easy. That's not a problem. You do need to have maintenance. We'll talk more about that. And then there's the cost of it. And even though it's not expensive compared to mechanical ventilation or even air conditioning for that matter, there is some cost associated with it. And it needs to be sustainable. not only maintenance, but basically replacement. Next slide. So we published a study from a study done, research done in South Africa a few years ago, and I need to put the reference on here, but Matsi Mfaleli is the first author, I'm the last author, where we showed that in a study of real patients with tuberculosis, probably could be done with COVID as well, but again, the airborne nature of COVID is not as clear as the airborne nature of TB, but basically we showed 80% efficacy, the equivalent of adding 24 air changes to a hospital ward where MDR-TB patients were residing, and we used real infection of guinea pigs as the outcome to demonstrate the efficacy of. I'm very sad to say this morning that you'll see here as an author Anton Stoltz, a very close colleague in South Africa, who passed away this week very prematurely, brilliant researcher and physician, and who became our major collaborator in the air facility in South Africa where this study was done. Next slide, please. So in terms of dosing, that study at the air facility led us to recommending as many as 17 milliwatts per total fixture output per meter volume, or cubic meter of volume. We've subsequently repeated the study and found that we got good efficacy with a lower dose. We're now recommending 12 milliwatts of total fixture output per cubic meter of room volume. I'll show you how it works in the next slide. So this actually still has the 17, but I can tell you what happens when you, so this room volume, 3 meters by 10 meters by 5 meters, we just simply take the 17, or in this case, the 12, and it tells us how many watts we need. If we use 12, it comes out to 1.8 watts and 4 fixtures. So we would put 4 fixtures in this upper room to disinfect that air properly. Next slide. Safety, the major issue is whatever radiation, or UV light bounces from the ceiling into the lower room. And we need this high intensity in the upper room to disinfect, and we don't want to exceed about 0.4 microwatts in the lower room. So you have to have a meter to make sure that the system is safe before you turn it on, and then it should be safe thereafter. But anyway, we're worried about people's eyes. Again, no serious complications from that. People don't stare at the fixtures, they walk around, and we've shown in other studies that I don't have here to show you that really people get a very small fraction of the allowable limit of UV in the lower room. Next slide. Next slide, please. Actually, this is a monitoring study that we published a while ago. This was back in 2005. And these are all individual patients and nurses and people in shelters and staff, teachers, and where UV was in use. And the highest level we measured for individual exposure was only 1/3 of the threshold limit value. Now, just for comparison, if you were outside on a sunny day in a warm part of the country, of the world, you might get as many as 240 milliwatts of millijoules per centimeter squared dose in that 4-hour period outside, 240. We allow 6 in the lower room. And the 6 is the less penetrating UVC compared to sunlight, which is much more damaging. So really, the lower room is quite safe in rooms that are being treated with upper room germicidal. Next slide. Almost done. You can see here with these fixtures how we keep the UV in the upper room. Whatever we measure in the lower room is simply by reflection from the ceiling. Next slide. Now, not all fixtures are the same. These fixtures with very close louvers are very safe, but they're also very inefficient. You can design fixtures better that are also safe. And you see this is tilted upward a little bit and put out much more UV. So this is 10 times more efficient than those fixtures. Next slide. So you need to buy good fixtures. They need to be measured for output. So this is a integrating sphere. One of our postgraduate students, and to measure how much comes out of a fixture. The company needs to do that, and they need to report how much UV comes out of a fixture before you buy it. Next slide. Another way to do that is gonioradiometry, where a fixture is hung in this is a lamp, but hung in the center of a device which measures UV coming out in all directions. Next slide. I put this slide here. This was a proposal that was not funded for India, but it was a proposal to try and have continuous technical support for UV with an outside company that you would contract with to come in and maintain the fixtures. It's not rocket science, but hospitals are really not very good at maintaining things. So once they're in the facility, you need to really have some way to ensure that they're going to be cleaned and the lamps changed on a regular basis. Next slide. Well, this is, I think, the next of two or three last slides, and I'm a little over time here, but the UV world has become more complicated lately. What we've been talking about is typical mercury lamps, which produce 254 nanometer UV. That's the wavelength. There are now two other wavelengths to be concerned about. There's LEDs, typical like the ones in your flashlight, which are coming online fast. Unfortunately, they produce a higher wavelength of UV, which is at the peak of causing irritation of the skin and eyes. So they have to really be done very carefully. And right now, they're still a little expensive. They probably will come into play in designer fixtures for restaurants and hotel lobbies to deal with COVID, and not so much in where cost is an issue. Because these fixtures, as you've seen, are not beautiful. These could be made quite nice, but they are more expensive. Then in the middle here, I have Excimer lamps, which are, that's not a brand name, it's a type, produce 222 nanometer UV, lower UV. This is remarkable because, and very exciting because it doesn't cause any eye irritation at all because it penetrates so little. It appears that it will do a good job at air disinfection. Because it can be shown directly into the room, it might cause some surface disinfection, but its limited penetration is also is a problem. So it may not get through ordinary oils in your hand that might be sheltering bacteria. Right now, these lamps, these 222, are hard to find. They're not being mass produced. They will be soon. The cost per watt produced is extraordinarily high at the moment compared to ordinary UV lamps or even LED lamps. And their exact role isn't clear, but they eliminate, even though ordinary UV is used quite safely, this can be used without safety concerns at all. So last slide really is that, I just wanted to show this is the peak of these are the wavelengths down here. So skin cancer and eye irritation are caused by higher wavelength UV, with the LEDs we're talking about in this range. So still pretty far from skin cancer, but enough to cause some irritation. 254 is very close to the peak of the bactericidal range. 222 is not, but it still seems to be able to work well enough. Next slide. This is a prototype LED fixture currently being tested in Pretoria for its efficacy. Again, longer wavelength UV. This is just a prototype. Other fixtures will be made to look better than this. Next slide. I think this is the, and this is the 222 UVs. You can shine it directly into the room. It's said to cause good disinfection. We haven't had any experience with it, but not likely to cause any eye irritation. But will it be as good or better than lower room? I think we don't really know. Next slide. Last slide. So we have now, things are more complicated. We have our conventional UV, works well. We haven't talked much about surface disinfection or disinfecting respirators or whatever. It can be used for that, but you have to be careful about exposure to 254. 265, 270 LED UV, you have to be even more careful because it is more likely to cause eye irritation. But with high ceilings in restaurants and hotel lobbies, it may have a role for making very nice looking fixtures. And then finally, this far UV 222, no eye irritation, can be used directly into rooms. Possible surface disinfection can be used with lower ceilings, but it's expensive and has limited penetration, may not do such a good job on surfaces, but should disinfect air. And with that, I'll stop.
Thank you very much, Ed, for the excellent presentation. And I'm sorry we started kind of a little bit late, and I was unable or maybe forget to introduce you. So if you may allow me to do the introduction.
Sure.
So yeah, sorry again. So Professor Ed Nardell is a professor in the Department of Medicine and of Global Health and Social Medicine at Harvard Medical School, and an associate professor in the Department of Immunology and Infectious Diseases and Environmental Health at the Harvard School of Public Health. He is an associate in medicine in the Department of Medicine at Brigham and Women's Hospital, BWH, in both the Division of Global Health, Equity, and the Pulmonary Division. His research interests involve the control of TB under resource-limited conditions, with a focus on the pathogenesis of MDR-TB, its airborne transmission and transmission control in institutions. He has recently tested interventions to prevent transmission of MDR-TB in a unique experimental facility in South Africa, in which large numbers of sentinel Kinebeg served to sample the air from a 6-bed MDR-TB ward. An early observation of the research led to new investigation on TB pathogenesis, specifically the possibility of the transient TB infection, as well as in pigs as well as humans. Professor Nardell also is developing more efficient, less expensive UBGI fixture for resource-limited settings. In addition, he has worked on developing and validating a computer-assisted design software package to facilitate the planning of UV installations in buildings. He has also begun testing a novel, environmentally safe chemical vapor that may be effective in reducing airborne transmission. So thanks again, Ed. I'm not sure. I know you have another commitments. Would you like to take questions now, or you have time to wait till we receive questions from the participants?
I will try very hard to get back to you so that we can do the questions at the end. This ends at 9:30, so I'll try to be back by 20 after, so if at the latest, maybe before then.
Okay, great. So now we move to the second lecture that we have. This is on application, or the second presentation. This is on application of upper room UVGI And our presenter is, let me look at the bio. I just received the bio. Richard Vincent. Richard Vincent applies GUV cleansing technology and tools to control the transmission of tuberculosis and in high-risk settings. He was the project manager and UV lightning specialist for TB, TB ultraviolet shelter study. That was from 1997 to 2004. This is a multidisciplinary, multi-center epidemiological field trial of ultraviolet air cleansing at the Aiken School of Medicine. He is working on reducing the rate of hospital-acquired infection by benchmarking the efficacy of various technologies, including mobile whole room UVC devices for decontamination of surfaces from pathogens such as MRSA and C. difficile. So, Mr. Vincent will proceed with the next presentation. Again, he serves as the coordinator for the Stop TB Partnership Working Group and TB Transmission Initiative (ETTI), where he provided expert input on GUV for WHO guidelines on TB infection prevention and control. 2019 update. Mr. Vincent is the chair of ASHRA, developing guidelines for the application of UVGI, GUV, and he chairs the CIE to test upper room GUV fixtures. So please proceed, Richard. Thank you. Hello. Hello.
Okay, can you hear me now?
Yes, we hear you now.
Oh,
thank you.
Okay,
so
I'm sorry about
yeah.
that.
No problem. I thought there was a problem with the Zoom link. So please proceed.
Okay.
Thank you.
Thank you. On the screen, you will see a corridor in a hospital in Pakistan, and you'll notice that the very tall, high ceilings are a very good opportunity to place upper room UVGI fixtures, also known as germicidal UV fixtures. You'll also see that there is a ceiling fan. I hope you can see the arrow as I'm pointing to these. And you'll also see the cutoff of the fixtures so that the beams of UV follow the blue light that you see here. UV is actually invisible, so you cannot see that, but it follows the same general pattern as the blue light that is being emitted from the fixtures. And corridors are all right, I guess that you cannot see the arrows, but I will talk and let you know what I'm specifically looking at. And corridors are one of the main areas that you would want to consider placing UV because they are places where transmission can go depending upon the triage. Okay, we'll go to the next slide. I can't move the slide, so could you move to the next slide, please? This is Dr. Brickner. He was a pioneer in the reapplication of upper room germicidal UV fixtures in high-risk settings of homeless shelters, and that was the tuberculosis ultraviolet shelter study that was discussed in my bio. Next slide, please. All right. Yeah, I guess we went too quickly. I'm sorry, these, could you move back, please? One more back. Thank you. Why should we, all right, next slide, please. Why should we use upper room UVC 254 nanometer systems now? It works well with both natural and mechanical ventilation combined with ceiling fans. It is about 80% effective in reducing the risk of transmission of airborne pathogens. It works against a wide range of airborne pathogens, including drug-resistant strains of tuberculosis, viruses such as measles, influenza, COVID, and it works against bacteria, spores, and fungi, although those are more difficult to inactivate with UV. And the maintenance of the systems are relatively simple, and human safety can be achieved with proper design, installation, commissioning, operation, and maintenance. Next. The WHO guidelines that were updated last year on TB infection control listed a series of interventions to be taken together as a package. And of course, when you apply upper room germicidal UV, it has to be within the context of a infection prevention and control plan that is developed by the facility. And this would be including the airborne precautions that you would want to develop as a part of that strategy. And you can see the WHO talks about triage, where people are separated, respiratory separation, prompt effective treatment, respiratory hygiene, upper room germicidal UV, ventilation systems, and then particulate respirators. All of these have to work in combination. UV is a supplement to all these others, and the most important, of course, is the administrative controls. And so UV always has to be in the context of a full IPC package. Next. You can see one of the concerns, of course, that we see in many places where we have crowded waiting areas that can cause a lot of transmission to occur. When you get into an area where on the lower part of the slide, you see so many people gathered together, even if you had a lot of UV in that space, it would not be effective because there's just such close contact. And so that's why you have to have the administrative controls to reduce the number of people in an occupied space. And then you can more carefully apply these environmental controls. Next. In the tuberculosis ultraviolet shelter study, we placed 1,200 of these UV fixtures in 14 different buildings, from mechanically ventilated to naturally ventilated. And over a period of 7 years, we were able to monitor these systems, maintain them, and to ensure safety. We only had one exposure problem, and that's where a double bed, a bunk bed, was placed too close to a UV fixture. And once the fixture was moved away from the bed, the problem was resolved. Next slide, please. So where should we consider applying upper room UVC systems today? In health facilities, the waiting rooms, emergency departments, places where you have specialized aerosol procedures inside. For tuberculosis control, if you have natural ventilation, a lot of the aerosol procedures can be done outside when you're doing sputum connections and use the available natural ventilation. But where you have to do specialized aerosol procedures, UV would be a good supplement to the natural ventilation or mechanical ventilation. Isolation rooms would be a good place. TB wards, operating rooms, autopsy. Many places are doing autopsy on COVID patients now, and so they need to have protection in those spaces because of the aerosols that may be generated. Places where x-rays are taking place, patient rooms, corridors. If you have vulnerable populations where they have compromised immune systems, such as those with transplants or cancer or HIV, In nursing homes, we know that the elderly were one of the largest populations that have been devastated by the COVID disease. So protecting the elderly in nursing homes would be a good place to consider UV. Dental clinics, where you have a lot of patient close-ups, urgent care clinics, prisons, and jails. So these are some places where you might consider putting UV. And you'll see the fixtures outlined in red in this medical ward. Next slide, please. The NTB Transmission Initiative has been working very closely with our partners in the Stop TB Transmission Initiative. And so they are looking towards, we're trying to put together documents that will be easy to understand and to really go into depth about various topics, from respirators to fit testing. And we put together a brochure on germicidal UV systems. And one of the key questions people want to know is, what do these systems cost, especially as people are putting together their applications for global funding for the next year. These brochures and technical information notes that are available at the ETT website would be a good resource for you to consider. And that website is listed here on the left-hand side of the slide. Next slide, please. Ed talked very closely about safety, and the TB-UV shelter study. We found that over a period of the 7 years, there was, as I mentioned, there was only one overexposure. And because it was a placebo-controlled trial, we were able to ask in both arms, whether it was active or inactive UV, whether there were skin or eye irritations, and we got equal amount of responses for both of them. So we knew that this, the installation was a safe installation. Also, the CIE has produced a review of the literature on the possible photocarcinogenesis of germicidal UV 254, and it found out that it can be safely and effectively used for upper air disinfection without a significant risk for long-term delayed effects such as skin cancer. And so that document is also available for free from the CIE for free download. Next slide, please. How does upper room UVGI work? It has to be combined UV with air mixing. And so you see that convective air currents carry any organisms that are floating in the lower occupied part of the room, and then flow those up into the UV disinfection zone. And as the organisms are inactivated by UV, then they come down into the lower part of the room and dilute the concentration of pathogens in the lower part of the room. Next slide, please. And Ed has talked about the fluence rate for the entire room volume. And the other principles, of course, with UV is you try to place it so you get the longest path length. In the lower left-hand side part of the slide, you will see fixture A mounted on a short wall will give you the longest pathway for the UV to travel. And UV is effective until it hits the surface either of an organism and gets absorbed, or hits a wall and gets absorbed. So the longer the travel path, the more opportunity for UV to hit an organism and inactivate it. And vertical air mixing is a must because it's considered, it transports the organisms from the lower part of the room to the upper part in a more efficient way. You can do it without, but it's more effective if you have the vertical air mixing. And that vertical air mixing can be either through the ceiling fans, or it can be through mechanical ventilation. Next. UVC lamps come in different shapes and sizes, as you'll see here, and then in the lower left part, the gold source is an LED, and there are some of those products that are floating around right now. They're not really ready for prime time in many areas, but they are something to be followed as more data is being developed. And so you will see that these are the most efficient way of producing germicidal UV is through a mercury vapor lamp, where 35% of the electrical energy is turned into useful UV. Next slide, please. The different UVC lamps can vary in spectra. So you need to have a radiometer as pictured in the right-hand side of the slide. Those are two examples of radiometers. And in the ETTI guideline information on GUV, you'll read more about these types of special radiometers with a detector that is set for measuring the accurate amount of UV at the specific wavelength that we're looking at. Because just because a blue light is on, you are not able to really tell whether germicidal UV is flowing from the light or not, unless you have a proper UV meter, also called a radiometer, to be able to test that. Next slide, please. And UV fixtures come in two different varieties, some that are more restricted with louvers for lower ceilings, and those that are more open for high bay areas. Next slide. These are some examples of the louvered fixtures. That the one on the left has compact germicidal lamps in it. The others have linear types of fixtures in them. Next. These are examples of open fixtures where you shine the light up into a higher bay area. The one on the far right is a fixture from Vladimir that has a lid on the top that can be adjusted to allow more or less UV to come out. And so it has a flexibility for a greater or lesser amount depending upon the ceiling height of the space. It also has an interesting component to it. There's a lamp on the bottom of the fixture that is turned on at various times to decontaminate the walls. So that's an interesting feature. In our assessment of a operating theater in India, we discovered on the bottom left hand that there were these fixtures up on the wall that weren't working. It turns out that they were older style germicidal UV fixtures, and so they were put in with the brand new lamps and they worked. And so these are some other interesting designs that various countries are adapting. Next, please. We found from our studies in India that reflectance of materials is very critical. In one of the installations, the paint on the wall was highly reflective of UV and created a safety hazard when we were doing our commissioning process. So then we were able to test various local paints and found a paint that was very low as far as its reflectivity of UVC 254 nanometer. And we repainted the facility, and that helped in our process as we were adjusting the system to make it safe for occupancy. Next slide. As Ed mentioned, we are recommending that all the germicidal fixtures, or luminaires is a more technical term for that, be tested by an independent lighting laboratory. And independent testing is available for these units, and many companies are getting their fixtures measured. You can see that as you look from left to the right, that you go from the electrical watts of Model A at 36 watts. It produces about 12.6 UV watts, but the fixture itself only emitted 0.22 watts. So you would look at that and you'd say that is a very inefficient use of the optics within the fixture. So the useful UV coming out of that fixture was very minimal. Whereas Model B had 25 watts of electrical wattage lamp producing 8.8 UV watts, but it had twice as much UV as it was measured initially, and almost 3 times as they improved the fixture. And then as you look at other models of UV fixtures, some of them have really improved their optics and get quite a bit of UV out of them. The lower 2 fixtures are the more open style of UV fixtures, and you can see quite a bit of UV is able to come out as they use more of the lamp output to fill the upper room. So ETTI is working with the GDF to help in the listing of germicidal UV fixtures so that people are able to go to a reliable source for some of these products to be available. So that's something that you can begin to look for. Next slide, please. So these are the ways of dosing today that we're considering. The volumetric approach is like step 1, where you determine basically on the back of an envelope how many fixtures you need based on the room dosing. And then there is a refinement to that by step 2, placing those fixtures within inside of a CAD program that is designed to use germicidal UV and be able to calculate what is the actual UV in the upper room. And 3, the third step is the safety step, where we go in before the system is switched on for occupancy and measure at eye level whether you have a safe eye level within that area. We can't go into all the details in this lecture, but there will be some other resources that we can point you to that you can learn how to do this type of a program. And then the 4th aspect is the air mixing for effectiveness. Next slide. All right, this got a little bit squished, I guess, in the process of converting all the slides together. But it basically is the dosing scheme that Ed was describing, where by applying this volumetric approach, you can achieve between 16 to 24 equivalent air changes per hour. So that would be a supplement to whatever ventilation was already available within the room. And as he mentioned, now we're recommending the lower dose of 12 milliwatts per cubic meter to apply as the dosing strategy. Next slide, please. We wanted to be able to develop a tool that engineers and architects could use, as many of them are very familiar with CAD-based programs. And there was a study done at St. Vincent's Hospital and Harvard School of Public Health, where we did some testing to verify this lighting software component using germicidal UV. This program is available for a complimentary license for those who are interested in applying germicidal UV using a CAD program, and you can contact me for further details. Next. One of the architects that was at a course that we were teaching at the Harvard School of Public Health picked this up very readily and imported a model that they were developing for a cancer center in Rwanda. And in SketchUp, they developed their 3-dimensional model and imported it into the CAD program, and were able to then plan the UV system that was eventually put into the facility. You can see in the right-hand picture the UV fixtures on the wall and being suspended from the ceiling in a large low velocity fan mixing the air. And this was a naturally ventilated space as well. Next slide. I'm not going to go into detail on this at this particular moment, but it's basically how you would go through first the volumetric approach and then comparing that to the computer program. And you'll find that as you go from the volumetric approach and then put it into the computer program, you may actually use fewer UV fixtures because you're able to calculate based on reflectance and other factors the average fluence in the upper room. And so this is the advantage of using the computer modeling process versus just the back of the envelope approach. Both would be acceptable, but I think the refinement of the computer program is an additional detail that is worth pursuing. Next slide, please. ETTI has designed a document in multiple languages, from English to Spanish to Russian and Chinese. And it is all about how do you maintain upper room germicidal UV fixtures. One of the big issues, of course, is many times UV systems are installed and then forgotten. But this is a way to actually build a sustainable germicidal UV program by planning for having maintenance, either by purchasing a service contract with a local vendor that is willing to come in and maintain these, or by training the hospital facility engineers how to be able to maintain these systems. And this document is also available from ETTI for free, and it is well worth obtaining because it goes into great detail about the types of meters, how to plan your maintenance program, and how to take monitoring measurements of these fixtures. Next slide, please. So in summary, we look at from left to right. This is an installed UV system in India, and before we are able to turn it on and switch it on, we go through the commissioning step, which is shown in the middle, where we're doing eye level and output readings of the UV fixtures. And then this is how it looks on the right, where it is an occupied area. And so that is the end of our lecture at this point, and we'll be open for questions later on. Thank you very much.
Thank you very much, Richard. This is really very, very good presentation. And now we'll proceed with the next presentation by Grigory Velkonkov. He will expand on an application of upper room UVGI and a summary, and I will proceed with some brief about Dr. Grigory, who is a Chief Doctor at Vladimir Regional TB Control Center in Vladimir, Russia, and TB infection control expert. Since 2002 until now, he is the head of Vladimir Regional TB Control Center and director of Regional TB Program. In 2002-2003, he moved the Regional TB Hospital to a new building and implemented and initiated TB infection control program supported by CDC, USA, and WHO control program in Russia Federation, which resulted in substantial reduction of occupational TB among healthcare workers. As a director of the center and faculty member, he participated in numerous training courses on TB infection control, engineering systems design, installation, commissioning and maintenance, TB laboratory biosafety and biological safety cabinet testing and maintenance. So Dr. Grigory, please proceed with the next presentation. Thank you.
Thank you, Hala, for introduction. And after we discussed upper room UVGI, the priority intervention for airborne infection control, recommended and recently updated WHO guideline on TB infection control, we'll discuss other application of germicidal UV, and these are whole room induct and air cleaners with UV. And this application are not as important for airborne infection control, but quite widely used in the world in many countries. So let's see what is it about. So first of all, next slide, please. The whole room germicidal UV. Next slide, you can see the picture of quite simple, inexpensive, old, actually maybe 30, 40 years old fixture, movable, with 6 30-watt nominal watt UV lamps, which can you see in older facilities in many countries. This is in one of the microscopy lab, picture made many years ago. They are still available and still used in many settings. So this kind of fixtures, now we can see much newer, much nicer, much more beautiful looking devices. But generally it's about the same. It's about irradiating of UV into the whole space of the room. And there are some drawbacks, some dangers, and some benefits of that. Next slide, please. We can actually see some advantages. They include very fast disinfection of air of the whole room and very fast disinfection of some surfaces in that room, which can be important for the contact precautions, for the contact infections like COVID-19. The second advantage is quite low cost generally, if you not take into account the modern robots. We'll discuss them later. So this whole room fixtures, they disinfect both air and surfaces, but not all surfaces, only unshaded surfaces. And also potentially it can affect very high areas or volumes in the space, like huge hangars can be disinfected in few minutes. The major disadvantage of the whole room UV fixtures that there is very high risk of overdosing of dangerous exposure of people in this room. So they for sure cannot be used in occupied spaces, areas, because of high risk of overexposure, because usually the flux or output, UV output of such fixtures is quite high, so it's dangerous to stay inside such irradiated room. Another important things to consider that only after effective and thorough cleaning of the surfaces of all the objects, they can disinfect the surfaces. We learned from previous lectures that UVC does not penetrate any objects deeply. So they only disinfect surfaces for microns in depth. So the thorough cleaning is required before using whole room UVGI. Also shaded areas are not affected for sure. There is no UV irradiation in shaded areas. And also, very important for airborne infection control to consider is that if the aerosols generated continuously, they cannot be effectively used at all. Next slide, please. So it's not actually airborne infection control intervention, I mean whole room UVGI. This is wall-mounted fixture with lower lamp open to irradiate the whole space. It's inexpensive, again, it costs about 20-30 US$. And again, can be safely used in procedure rooms, in operation rooms, without people inside this room. Next slide, please. So these two pictures are expensive and modern looking, but basically the same devices for whole room irradiation. They're called UV robots already. They can move, they can be programmed, they can change the height of the source of the irradiation. And ads say that UV bacteria killing robots cleans hospital rooms far better than humans. But I think you agree with me that without humans, they cannot effectively work. Again, thorough cleaning before UV whole room disinfection is absolutely required, because any kind of remaining grease, remaining dust, it will protect the germs, the viruses from effective disinfection by UVC. Next slide, please. So this is another kind of device, but also whole room UVGI. But it uses also mercury, but impulse irradiance with a very high intensity. And the wavelength is not just 254 nanometers, but wide from 2000 to 200 to 800 nanometers. So it includes lots of UVA, UVB, UVC. So again, it's for instant irradiation and high volumes of spaces. Now this device is owned by my hospital, and we actually let other COVID infectious disease centers, which are active now, to disinfect air and spaces after they move patients and staff out. So it's quite an expensive device, but again, not quite useful for actual effective airborne infection control, and very costly, you can see. So to use it, you just enter the volume of the space in cubic meters. It calculates the required exposure using the programmed dosage for most common pathogens. Next slide, please. Another kind of whole space UV is UV lamps installed in biosafety cabinets. So it irradiates in the whole space of working area, limited space inside the cabinet. Again, it's not part of the international standards for biosafety cabinets, not European standard EN 12469, not US standard. They do not require to have such UV lamps. It's just an option. And again, it does not replace the thorough cleaning and use of disinfectants for working area of the biosafety cabinet. So it's not primary intervention in this case for laboratory biosafety. Next slide, please. Another example of use of whole space UVGI is shown on the next slide. Is sputum collection booth. It's again negative pressure, limited space booth, where aerosol high-risk procedure takes place, collection of sputum from TB patient. And when the patient leaves the booth, both mechanical ventilation with high ACH and whole space UVGI, they disinfect, they reduce the concentration of viable particles, bacteria or viruses in this limited space in very, very limited time, just in couple minutes. Next slide, please. So what's required to use effectively a whole room UVGI? So first of all staff, healthcare workers, patients should be educated about the dangers and positive sides of UVGI in whole room. We should put appropriate signage, warning signage. Do not enter while UVGI is on in the room, and warning lights at the entrance of the room are required. Maybe sounds in some cases. So the unit for whole room UVGI should be equipped with the remote controls. We cannot operate the device while we are in this room because of high risk of overexposure. We should use protective glasses if we enter such room for sure, because photokeratitis will be instantly the fact for the person who enters. We should determine optimal exposure time for every room based on actual UVC output of the fixture, using the dose and calculating from the remote corners distances, remote objects distances from the source. We also should determine and develop indications, conditions for the procedure, like SOPs for staff, when, where, how to use such devices for room, air, and objects disinfection. And we should ensure a regular lamp and reflector cleaning by alcohol solution 70%, and also regular lamp replacement according to manufacturer recommendations. Next slide, please. How can we calculate required dose or required exposure time for disinfection of air using the open source of UV? So we have to consider what is wavelength we use in the device. And Ed already told there are most commonly used 254. There are far UV is just emerging. There are wide range like this impulse sources, also low intensity sources are but expensive, also available. So we have to consider what kind of UV, what's part of spectrum they are from. Also, pathogen susceptibility is extremely important to consider. There is a special characteristic of that called Z-value. Z-value is ratio of inactivation rate normalized to the average irradiance. For most of the pathogen, it's known, it's published. Next slide, you'll see the data about MTB. I think that SARS-CoV-2 virus have not actually determined yet the Z-value, but we can consider the other coronaviruses and actually add to be sure that the irradiation is effective. We should consider the required inactivation rate, like we plan to reduce the concentration of viable bacteria on surfaces in the air by 10 times, 100 times, 1,000 times, so on. So for any this inactivation rate, we can find the required total dose. Important factor to consider for some southern countries, especially, is air relative humidity. We have to understand that with humidity, relative humidity higher than 80%, the susceptibility of pathogen can change, can actually be higher quite substantially. So simple formula tells that dose equals irradiance multiplied by time or by exposure. So we can easily calculate required exposure time if you know the irradiance, which can be easily measured by radiometer. Richard just told us about that. And if we know the dose required for disinfection of particular pathogens. Next slide, please. So for MTB UVC dose, you can see that we'll reduce the concentration, actually the risk of transmission, by 100 times or 99% if we deliver 10,000 microjoules per square centimeters. So knowing the irradiance measured by a radiometer, we can calculate for the particular source of the UVC required exposure time for the disinfection, for reducing the risk by 100 times. Next time, please. So this data is published for most of the pathogens. So let's discuss the next possible application is induct UVGI. It's also quite old technology utilized in public buildings, in subways, and it's used in ducts of supply ventilation systems to disinfect the supply air in some settings. It can be utilized in healthcare facilities and public buildings to disinfect recirculated supply air. It can be used in laboratories in high-risk areas for exhaust air treatment to reduce the risk of exhaust of infectious aerosols from high-risk areas. So how it works? Next slide, please. Inside the duct, the engineers installed powerful UVGI lamps. How many lamps? What's total UVC output for these lamps? It can be calculated by engineers, and they take into account the flow rate, volume of air per hour or per second. So they actually find out how much time any particles will spend in the irradiated zone of the duct when air moves through this UV induct unit. Next slide, please. The drawback, possible drawback of such application can be failure of such induct units, and if we install it into the recirculation contour, or recirculation duct, we can introduce actually infectious air back inside the building, and it can be actually of very high risk of transmission of airborne infections, TB or COVID. So generally, if the resources do not allow quality maintenance of the system, if there is a risk of failure of such units, we should not plan such interventions in high-risk facilities. This table shows the calculation of the comparative costs of HEPA filtration of air, installing filters, quite expensive, and UV treatment in ducts of the air. So it shows that actually much less expensive, but also very, very effective in terms of reduction of viable pathogen in the air. So depending on how much UV we deliver into the duct and depending the flow rate in this duct, we can achieve very, very high rate of effectiveness equal to HEPA filtration of the duct and save actually lots of resources on maintenance and replacement of filters or lamps. Much cheaper intervention. And mostly it's recommended for airborne infection control as a safe exhaust from high-risk areas, for example, from BSL laboratories, if national recommendations dictate us to use some kind of infectious air treatment for exhaust from high-risk areas. Next slide, please. So next part and last part of my presentation is room air cleaners with UV. It's growing market, very aggressive market, and far upper left unit is Russian UV air cleaner called Desar. Others are hybrid and other kinds of air cleaners, but we are interested to see what's about UV inside this box actually. Next slide. And in fact, such UV boxes include UV source, reflector inside, and the fan, which supposed to move air from the room into the irradiated area closed into this device. So Paul Jensen, who is actually among the listeners of this webinar, demonstrate how air of the room is affected by this device. And you see that the smoke actually goes not affected by the unit at all. Next slide, please. But the unit is switched on, and when Paul removed the cover, he found that the computer-like fan moves the air from irradiated zone inside the box out of the irradiated area into the internal space of the air cleaner. So no any airborne particles affected in the whole space of the room. And you can say that the risk is zero inside this air cleaner, but the risk is not affected, it's still maybe high in the whole space of the room for occupants. Next slide, please. Another example of the engineering failure. So this is the recirculation of the air inside the box. Another example, UV air cleaner. It has a UV source, the simple lamp covered by plastic. So plastic is not penetrated by UV. So this unit is useless regarding airborne infection control and consumes some energy, gives some sense of protection, but in fact does not make any effect on the concentration of viable pathogens in the air. Next slide, please. The next problem with air cleaners is their low clean air delivery rate. Ed Nardell already told you about the CADR, the very essential characteristics of air cleaners. And this is Russian air cleaner, and the advertising in the internet published by the manufacturer. So next slide, please. If you see on the lower part of the presented graph, shows the effectiveness in the reduction of the concentration of the pathogens in the air colony forming units. So if we recalculate the rate of reduction of colony forming units when the air cleaner is on, we can easily calculate the effect on the concentration of pathogens in the air equals actually only quarter of equal ACH, air changes per hour. So I would say that it's just almost zero effect on the airborne infection concentration in the air. Next slide, please. So basically the message is, if you decide to use air cleaners, find out about CADR, clean air delivery rate, which is simply calculated by manufacturer. We cannot actually determine it easily. It should be laboratory testing. So it's physical flow rate in cubic meters per hour multiplied by contaminant removal rate or particle removal and activation rate. Actually, UV does not remove particles, it inactivates pathogens by affecting the DNA or RNA. So this CADR can let us calculate equivalent ACH in the room required. And again, the goal is to have at least 6, the optimal is 12 ACH in the room. When we calculate a number of air cleaners just shown in the pictures, in the patient, one single bed patient rooms requires to have up to 40 air cleaners installed on every wall of such room. So the general message, theoretically, these devices can be effective, but in practice, I've never seen any effective with high CADR air cleaners able to reduce the risk of airborne infection. Thank you. That's my last slide. So can you hear me?
Yes.
Richard, can you continue some questions from participants?
Yes. So the questions up on the slide, the first one, does GUV need to be applied everywhere for public health? And no, it needs to be considered as a part of a risk analysis of your facility, where you go through and do a facility infection control plan with Airborne IPC as a part of the overall infection control plan of your facility. It is applicable for upper air disinfection. It can also be used, as Grigori was saying, if you have mechanical ventilation systems, you can apply it there for recirculated air in the facilities. And then in specialized areas where you're concerned about surface borne contamination, as in the COVID, with it is concerned as a adjunct to manual cleaning of those spaces. So UV is always a supplement either to ventilation or to manual cleaning in various facilities. So that has to be part of the standard operating procedures. How long does GUV last?
Richard,
yes.
I would say that I hope the humanity will learn from this pandemic, this airborne infections, and the next airborne infection. They need we need to learn from this experience that we do need effective environmental controls, and GUV is an expensive and potentially very effective interventions, low cost. So I hope it will be not just in healthcare facility, but in many public buildings in future.
Very good. I think that's very well said, that we need to consider it in various places for public health.
Thank you, Richard and Gregory. If there's any questions from the participants, please feel free to use the Q&A. Otherwise, I think the next question was, how long does GUV last with proper maintenance?
If you're interested in my personal experience, we have fixtures which were installed like 16 years ago. Some plastic in time, internal particle parts of the fixtures can deteriorate in time, but they last much time. And for sure, the good maintenance is required, lamp replacement, cleaning, and so on. But this is really long-lasting equipment.
I would agree with Grigori, is that many of the quality upper room fixtures can last up to 15 years as far as the actual housing of the fixtures, and maybe they will need to have the ballast that drives the electricity flow to the lamp replaced. But with regular maintenance, a lot of these pieces of equipment can last for long periods of time. In our ETTI GUV technical note, we put in a life cycle maintenance at 15 years. So you can see that many of these can last for up to 15 years before having to consider replacing them. But the regular maintenance of the lamps and cleaning of these is critical, because as we've learned that UV is very non-penetrating, so it's critical to keep the lamps measured for output and cleaned from dust and grit that can build up over time in these various areas.
I see the question from participant Sabank Malefi. How and which applications of UV can be used in context of COVID-19? So I would say that the choice is upper room UVGI for sure. because we actually talk about the airborne component of the transmission of COVID-19, and I believe it's actually very major component of this pandemic. And this is the intervention proven to be effective for airborne infection control.
Thank you so much, everyone. I see I have a question that privately sent to me. I'm not sure if it is there. I don't see him, but I think that's for his presentation related to key parameters necessary for effective UBGI system and resource limited settings. Grigori, would you like to take on this?
In resource limited settings, again, along with the natural ventilation, this is the intervention of choice because of low cost, easy maintenance. The critical is good maintenance, understanding of the technology, use of radiometer, lamp replacement, lamp cleaning. Installation is critical. But again, this is expanding the technology and all over the world, and I believe the critical components is good installation and good maintenance.
Great, thank you. Another question is related to the benefits and harms associated with the use of ultraviolet radiation in the prevention of TB. I think Ed and you all elaborated more on the benefits. Can you maybe elaborate on the harms associated with the UBGI?
I think I did mention in the
Yes.
tuberculosis ultraviolet shelter study that we did have one overexposure, which exceeded the threshold limit value established for eye irritation. And if you do look directly at a UV source, you can get eye irritation. It's like grit in your eyes from being on a beach, a sunny beach. And this is basically photokeratitis, and that resolves within a 24 to 48 hour period of time with no direct harm to the eyes. Also, you can get a skin erythema if your skin is exposed to UV-C radiation directly for a period of time. It depends on how close you are to the source as to how quickly these symptoms will occur. But again, none will have long-term effects at the 254 nanometer wavelength. As you get higher up, more 265, 270, where some of the new LED technology is looking, the skin and eye irritation becomes a greater concern. As you go below 254, down into like the 220, 222 nanometer range, you would have very low skin irritation or eye irritation. So those are the concerns. All these issues can be resolved by, if you have to work around UV sources, you can wear plastic safety glasses, which will block the UV from getting to the eyes, and you can cover the skin with normal clothing and gloves if you have to be around the source directly. But we don't recommend direct irradiation of any skin or eyes by UVC.
Great, thank you. I have a question, but I would like, because we have, I think, last by 5 minutes, we have Carrie also with us. Carrie is the She's currently serves as the chair of Stop TB Partnership and TB Transmission Initiative Working Group, and has served as the program secretary and now the chair of Nurses and Allied Professionals subsection of the International Union Against TB and Lung Disease. She's with us also today. Carrie, would you like to say something, elaborate on any points or any of the topics presented this morning?
Thank you, Hala. No, I think that I realize that we've gone over time a little bit, but I just want to thank everyone for joining in today. And this is not the last webinar that we hope to do, and we'll plan some more on more practical implementation issues around GUV and other infection prevention and control practices in the coming weeks, and we'll keep everyone posted on that. But thank you again for joining, and thank you to all of the speakers.
Thank you so much. We have also Paul. Paul, would you like to say something, elaborate on any points discussed this morning? Paul Jensen.
No, I think the speakers have handled it well. Thank you.
Thank you so much. Thank you so much, Richard, and thank you so much, Gregory, and Ed, Paul, Carrie, and everyone, and thanks to you all. And
I see last question from participants.
Oh yeah, please go ahead.
If UV kills my plants, how do I know is it safe for me? Serious question. So we do not have any senses of UV. We cannot see, we cannot touch, it doesn't smell. The only way to check safety and effectiveness is measuring by radiometer. So the measurement is absolutely required if we work with UV. Thank you.
Right, and in the form of UVC that we're talking about is not a wavelength that plants use for photosynthesis. So normally UVC is filtered by the atmosphere. Although it's produced by the sun, it is filtered by the atmosphere. So plants are not adapted to be exposed to direct UVC. So we recommended any of your plants that you would have in a UV installation be kept on your desk. Thank you.
Thank you.
Thank you so much, everyone, and we'll connect soon on other webinars.
Thank you so much.